I figured might as well start. Good afternoon, good morning, good evening, good middle of the night, good whatever time it is where you are. Welcome to the third plenary talk that we're running as part of the Student Symposium in Combinatorics. For those of you who are joining from the public, and maybe this is your first time here, this is a symposium run by students for students of combinatorics and combinatorics adjacent disciplines to get to know each other and see what kind of research is being done by your colleagues out in the wider world. We're very thankful to be supported by Matrix, which is a mathematics institute in Australia, as well as OSTMS, AMSI, and UNSW Sydney. It is my great pleasure to introduce our new plenary speaker, Peter Bradshaw. Peter did his undergrad at the University of Kansas and a master's at Simon Fraser University before starting his PhD at Simon Fraser in late 2020. Despite being relatively early in the grand scheme of things in his PhD, he has an impressive publication record surrounding graph coloring and graph games. For example, his master's thesis studying cops and robbers on Cayley graphs. And he uses tools from graph theory, but also probabilistic tools and algebraic tools as well. On top of all of these things, Peter apparently speaks 4 languages and reads German on top of that, which surprised me a lot. I'm hoping this talk's in English because I'm very, very keen for it. The other thing I wanted to say, in the spirit of the conference, one of the reasons that we got this whole thing set up was for collaboration. We wanted to encourage collaboration between students around the world. Personally, there's one collaboration that I'm really hoping comes out of this, and I know a lot of the committee, the organizing committee, are thinking similarly. We really hope that Peter Bradshaw collaborates with another particular conference goer, an old friend of the University of New South Wales by the name of Peter Bradshaw. There are 2 of them here, and we really hope that they can find some common ground. We really hope that they meet and can publish the Peter Bradshaw theorem. I know that theorems don't normally come with first names attached, but I feel like we can all agree that this would be a worthwhile exception to that rule. And I will also say that before the entire time leading up to this plenary, I was worried that I had prepped a speech about the wrong Peter Bradshaw. So I'm really hoping I got this one right. So today, Peter will talk to us about graph coloring and the Lovasz Local Lemma. Peter Bradshaw, I like that. About graph coloring and the Lovasz Local Lemma. And without further ado, Peter, take the proverbial floor.
All right, thank you so much for that introduction. Yes, you did prepare about the correct Peter Bradshaw. Yeah, so there we go. Okay, so yeah, thank you for the introduction, and thank you also to the organizers of this conference. I saw the plenary talk yesterday and it was a lot of fun, and I think it's great that we can have this student conference where we can all come together and we can talk about combinatorics and just have a good time. And I'm really happy to be invited. So I'll be speaking about the Lovasz Local Lemma. We saw a little bit about the Lovasz Local Lemma yesterday in the plenary talk, but let me give you my sales pitch for why you should care about the Lovasz Local Lemma. So I think there are 2 main reasons why you should care about the Lovasz Local Lemma. The first is that it's applicable to very many areas of combinatorics. Most often, if you see the Lovasz Local Lemma in the wild, you'll see it involved in a graph coloring problem. However, it has been used in problems about Hamiltonian cycles. It's been used in order to find strategies or show the existence of strategies in combinatorial games. And it's been used to answer questions about arithmetic progressions, specifically van der Waals numbers. And one thing I didn't add to this list, but I realized I should have, is it can be used in Candy Crush. The second reason that I think you should care about the Lovasz Local Lemma is, despite being a very simple tool that's very easy to learn, it's also extremely powerful. And here I've just made a list of problems where my co-authors and I were able to find a new result and where the Lovasz Local Lemma was a part of our proof process. And these first 6 results that I've listed here, they all have something to do with graph coloring. So like I said, this lemma is mostly used in graph coloring problems. However, The seventh problem on this list about list avoiding orientations. This is a problem where we have a graph and we want to orient its edges so that the out degree of each vertex does not belong to some forbidden list. And this problem has nothing at all to do with graph coloring. So the point of me emphasizing this specific problem is that even if you don't work in graph coloring and if you're in some completely different area of combinatorics, it's very likely that you can still use the Lovasz Local Lemma in your research. So without further ado, let me state what the Lovasz Local Lemma is. So the Lovasz Local Lemma is a probabilistic statement. And so to use the Lovasz Local Lemma, first you have a set of bad events. And I call these events bad because these are events that we would like to avoid. And we say that each bad event in our set of bad events is dependent with at most d other bad events, and each bad event has probability at most p. And the Lovasz Local Lemma states that if this upper bound p for the probability of a bad event times this upper bound d for the dependencies of a bad event, if this product is at most 1/4, then with positive probability, no bad event occurs. We saw in the plenary talk yesterday, this lemma does have a few stronger forms, but I'll just be talking about this most basic form because I think it's the easiest to understand. And the reason that the Lovasz Local Lemma is so useful is because if we have a combinatorial structure and if we want to look for some substructure that avoids certain properties, then what we can do is we can try to choose that substructure through a random process. And if we get the structure that we want with positive probability, then that must mean the structure that we want exists. So usually when the Lovasz Local Lemma is used, it's not used to show that something happens with positive probability, rather it's used to show that something exists. And so since you can set up these simple conditions, and from these simple conditions, you can get an existence statement, the Lovasz Local Lemma therefore is very powerful and can be applied very generally. So just to give everybody an example of how the Lovasz Local Lemma can be used, let's look at this example from hypergraphs. By the way, I took this example from the book of Malloy and Reed about graph coloring and the probabilistic method, but I'm not going to say that I'm stealing it because those two authors, they said they also took it from other places and they say it's the best example. So I thought if it's the best example, I have to use it. So this is a theorem about hypergraphs. If you're unfamiliar, a hypergraph is a set of vertices and a set of edges, but rather than in a traditional graph, in a hypergraph, one edge can contain many vertices. So here I have a picture of a hypergraph and each of these blobs contains 5 vertices, but for each of those blobs, we're just going to call it an edge. So we have a theorem that states if we have a hypergraph, each edge has size k, so it has k vertices, and if each edge intersects with at most 2 to the k minus 3 other edges, then our hypergraph H can have its vertices colored with 2 colors so that no edge is colored monochromatically. And the way that we can prove this is using the Lovasz Local Lemma, and it's actually not very hard. What we're going to do is we're going to have 2 colors. Let's call them black and gray. And for each vertex, what we're going to do is we're just going to flip a coin. If the coin lands on heads, we'll color the vertex black. And if the coin lands on tails, we're going to color the vertex gray. And we just go to every vertex in this hypergraph, we randomly color it, and this gives us a random coloring at the end of the process. Now what we can do is we can think about the things that we don't want to happen, namely we don't want any edge to be monochromatically colored. So we can say for each edge in our hypergraph, we define a bad event, which is the event that this edge is monochromatically colored. Since each edge has k vertices, it's not too hard to show that the probability that a given edge is colored with just one color, this is 1/2 to the k minus 1, because the first vertex can be colored whatever you want, but the other k minus 1 vertices need to be colored with the same color. So that probability of that bad event is 1/2 to the k minus 1 or 2 to the minus k plus 1. Similarly, since each edge is intersecting at most 2 to the k minus 3 other edges, we also have this upper bound for the dependencies of our bad events. So if we multiply our p times our d, what we see is that this is at most 1/4. And hence we get the two coloring of the vertices that we want with positive probability, or in other words, the two coloring that we want must exist. So this is just a classic example of how the Lovasz Local Lemma can be used to get some structure randomly, to show that the structure we want exists with positive probability, which shows that the thing that we want exists. Okay, so I hope this warms everybody up to how the Lovasz Local Lemma can be used. As you can see, it doesn't have to be very hard. The statement is very simple. The steps that you use in the Lovasz Local Lemma can also be very simple. All you have to do is define a random process, define your bad events, upper bounds P and D, and then multiply them together and you're done. So what I'd like to do now is I'd like to look at some examples of important results that have been proven using the Lovasz Local Lemma. And these results are not at all trivial, and I think they're very nice results. So the first result that I'd like to look at is this theorem of Alon, McDiarmid, and Reed from 1991 about acyclic colorings. So if you're unfamiliar, a proper coloring of a graph is a coloring of the vertices of a graph so that no two adjacent vertices have the same color. Now, if a graph has a proper coloring so that no cycle is colored with only two colors, then we say that the coloring is acyclic. So for example, in the picture that I have here, this cycle is colored with just the colors red and blue. So in an acyclic coloring, you would want to avoid anything like this. Now, it's not very hard to show that if you have a graph G of max degree delta, then at most delta squared plus 1 colors are needed for an acyclic coloring. But Erdős conjectured that delta squared plus 1 is too big, and he conjectured that this upper bound on the number of colors in an acyclic coloring can be brought way down. And in 1991, this conjecture was proven by Alon, McDiarmid, and Reed using the Lovasz Local Lemma. And what they showed is that if G has max degree delta, then in order to get an acyclic coloring, all you need is about delta to the 4/3 colors. And the way they proved this using the Lovasz Local Lemma is what they defined a set of about delta to the 4/3 colors. And then just like we saw in the previous example, they said, we're just going to color each vertex uniformly at random with one of our colors. Then what they do is they define a bad event at each cycle, which is the event that this cycle is two colored. They also define a bad event at each edge, which is the event that the two endpoints of the edge are colored with the same color. And then they have a few other bad events that they include for technical reasons. But after defining all these bad events, all they have to do is stick everything into the Lovasz Local Lemma, and this upper bound of delta to the 4/3 is proven to be high enough. And I should point out, they did use a stronger form of the Lovasz Local Lemma, and I swept some of the details under the rug, but the overall process is the same. They define a random process, they define their bad events, they upper bound probabilities and dependencies, and then just stick everything into the Lovasz Local Lemma and get the answer. I also want to point out, recently I was able to show an extension of this result of Alon, McDiarmid, and Reed. I was able to show that if you want to give G a proper coloring so that only the cycles of length M or greater cannot be two colored, then the number of colors that you need for this can actually be brought down to about delta to the M over M minus 1. And this is a generalization because the shortest cycle that can be properly two colored is the 4 cycle, like shown here. So if you plug in M equals 4 to that result on the bottom, you get the original result of Alon, McDiarmid, and Reed. But if you're okay with having your short cycles two colored, then the second result is stronger than the first one. And the way I was able to prove this was just by essentially copying their approach with the Lovasz Local Lemma, but just defining my bad events differently. So I defined a bad event for each long cycle in my graph, and I said a bad event is that this long cycle is two colored. Then I defined some other bad events for technical reasons. And again, using the Lovasz Local Lemma, everything came out easy peasy. So this is just to show you that like even conjectures of Erdős can be proven using this very nice general tool of the Lovasz Local Lemma. The other background result that I'd like to show, I chose this one because this has nothing at all to do with graph coloring, and I don't want to give people the impression that the Lovasz Local Lemma is only good for graph coloring. This result is a theorem of Karsten-Thomassen from 1998. And the reason that this theorem of Karsten-Thomassen is so great is because it's a step toward a problem that's been open for a long time and is still open today. And that problem is Jiang's conjecture. So Jiang's conjecture states that if you have a graph where every vertex has degree 4 and the graph has one Hamiltonian cycle, then it should follow that the graph has a second Hamiltonian cycle. And while this is still open, what Thomassen was able to show is that if you have an M regular graph, so every vertex has degree M, and M is at least 300, then if your graph has one Hamiltonian cycle, then it should have a second Hamiltonian cycle. And the way that Thomassen proved this was again using the Lovasz Local Lemma. So what Thomassen observed is that if you have a graph of the Hamiltonian cycle, you can draw all the edges of the Hamiltonian cycle in red. And then you can draw all the remaining edges in blue. And then if you can find a set of bolded vertices like the one that I drew here, where that set is red independent and blue dominating, then the existence of this set will give you a second Hamiltonian cycle. And when I say red independent, I mean no two of those bold vertices are joined by a red edge, and every vertex in the graph has a blue neighbor in the bolded set or is already in the bolded set itself. So Thomassen shows if you can find this red independent blue dominating set of bolded vertices, then you must be able to get a second Hamiltonian cycle. So then how does he get this red independent blue dominating set? Well, he uses the Lovasz Local Lemma again. He just says, I'm going to choose a vertex subset of my graph at random. I'm going to define a bad event, which says that two bolded vertices are joined by a red edge. I'm going to define another bad event that says some vertex is not in the bolded set and it has no blue neighbor in the bolded set. And then after defining these bad events, he just upper bounds probabilities, he upper bounds dependencies, and then he throws everything into the Lovasz Local Lemma. And by throwing everything into the Lovasz Local Lemma, this great answer comes out. And he shows that if the regularity of the graph is at least 300, then you definitely do get the second Hamiltonian cycle. And I just want to point out, I really like this result. I think the proof of this result is very beautiful. And I really recommend that anybody who's interested in Hamiltonian cycles look at this result. If you want to find it, just search Karsten-Thomassen second Hamiltonian cycle and you'll find the paper. It's published in JCTB. It's a beautiful proof. Okay, so these are my background results about the Lovasz Local Lemma. I hope this convinces you that it can be used to prove some very nice results. What I'd like to talk about now are two problems in which I was able to use the Lovasz Local Lemma in order to make progress on open problems and find new results. So the first problem that I'd like to talk about is the problem of single conflict colorings, which is a special type of graph coloring problem. So first, let me define how this problem works. In this problem, we have a graph and we have a set of colors, which we're just going to call the numbers 1 through k. And at each edge of our graph, we're going to put an ordered pair of colors, which we call a conflict. And our goal in this problem is to color our graph so that no edge is colored in the same way as its conflict. So for example, this edge on the right in the picture that I have here, its conflict is blue, blue. So we would not want to color both of those vertices blue. However, it would be okay to color both of those vertices red because the conflict is not red, red. So coloring both of them red would be okay. Similarly, for the edge on the left, the conflict shows blue at the top and red at the bottom. So we would not want to color the upper left vertex blue and the lower left vertex red. It would, however, be okay to put red at the upper left and blue at the lower left, because conflicts are ordered pairs. So we just don't want to color the two vertices at an edge exactly the same, including order, as their conflict. So if we can find a coloring of a graph using the colors 1 through k that avoids all of the conflicts, then we call this coloring a single conflict coloring. And if a graph G always has a single conflict coloring when the colors 1 through k are used, then we say that the single conflict chromatic number of the graph is at most k. So that's what that symbol there means. That's the single conflict chromatic number. And just to make it clear what this means, if I have a graph G and I claim that the single conflict chromatic number is at most K, then that means I could give you the graph, I could give you the colors 1 through K. You could be as evil as you want to and put the conflicts on the edges of the graph however you want. And then no matter how evil you are, if you give me back the graph, I should still be able to color the vertices of the graph using the same colors 1 through K without coloring any edge like its conflict. So this is what it means for the single conflict chromatic number of a graph to be at most K. And this problem was invented by those 4 authors on the screen fairly recently in 2018. Now, one of the questions that these inventors of the single conflict chromatic number asked was about the relationship between this parameter and a graph's degeneracy. And if you're not familiar with what a graph's degeneracy is, I'll just define it quickly using this picture on the screen. So if you look at the vertices of this graph on the screen, you'll see that some of them have degrees that are larger than the others. For example, the first vertex has degree 4, the fourth vertex has degree 5. Some of them have degree 3. But if you count how many left neighbors each vertex has, you'll see that each vertex has at most 2 left neighbors. So since the vertices of this graph can be ordered so that each vertex has at most 2 left neighbors, we say that the degeneracy of this graph is at most 2. Similarly, if I have a graph and I can order the vertices so that everybody has at most D left neighbors, then I say that the degeneracy of the graph is at most D. And using a greedy argument, it's fairly easy to show that the chromatic number of a D-degenerate graph is at most D plus 1. And using the same type of greedy argument, you can show that the single conflict chromatic number of a graph is also upper bounded by degeneracy plus 1. I'll be using D of G for the degeneracy of a graph. But what these authors asked is they asked if this upper bound of D plus 1 can be improved when a graph doesn't have too many vertices. And the reason that they asked this specific question is because if they could get a yes answer to this specific question, then it would help them prove another one of their results that they had about planar graphs. But I thought that this question was very interesting on its own, and I wanted to try answering it. And so did my co-author Tomáš Masaryk. And what we were able to show is that if you have a simple graph G, so no parallel edges, then the answer to this question of Dvořák, Esperet, Kang, Ozeki is yes. The single conflict chromatic number can be bounded above by about root D log D delta, where D is the degeneracy and delta is the maximum degree. And the way that we proved this was using the Lovasz Local Lemma. But as we're going to see here, when you use the Lovasz Local Lemma, everything doesn't have to be as easy as I made it seem in the previous slides. There can still be a lot of room for creativity and creative arguments. And this is what we're about to see. So what we did is let's start back at the beginning. We have a graph. The graph is D-degenerate and it has max degree delta, and we have our color set, which is colors 1 through K. And we would like to show that K doesn't have to be too big. Namely, K doesn't have to be much bigger than root D log D delta before we can guarantee a single conflict coloring on the graph G. So what we're going to do is we are going to randomly color the vertices of G, but we're going to use kind of a roundabout process in order to randomly color our vertices, because this roundabout process will make it easier to use the Lovasz Local Lemma. So what we're going to do is, rather than just randomly giving each vertex in our graph one color from the set 1 through K, we're going to give each vertex a random inventory of colors. And this idea of giving each vertex a random color inventory, this actually wasn't our idea. It was kind of copied from a paper of Aharoni, Berger, Chudnovsky, Havet, and Jiang for a different problem. But this was the first application of this technique to the single conflict coloring problem. But the way that we gave each vertex in our graph a random inventory of colors was, it was through the following random process. So we have our color set 1 through k. And for each vertex v, what we did is we considered each color in this set 1 through k. And for each color, we flipped a coin. And essentially, we consider the color 1, for example. We flip our coin. If the coin lands on heads, then we put the color 1 in the random inventory at v. But if the coin lands on tails, then we don't add the color 1 to the inventory at v. Then we go to the color 2, we flip our coin. If it lands on heads, we put 2 in the inventory at v. If it lands on tails, then we don't. And we just repeat this for each color in the set. And by doing it this way, each vertex gets a random inventory of colors. Also, I should say, we don't do a half and half probability for each color. We chose a value p that made things work nicely later. After we do this, we end up with a situation where we have a graph. Each vertex has conflict, each edge has a conflict on it, and then each vertex has a random color inventory. And what we would like to do now is we would like to change this problem into a sort of list coloring problem, so that we're going to try to give each vertex a color from its inventory in a way that satisfies a single conflict coloring. However, if we just arbitrarily assign each vertex a color from its inventory, then of course we might accidentally color some of the edges in our graph like their conflicts. For example, this vertex on the left here, we see that it has yellow in its inventory. The vertex V on the right, we see that it has red in its inventory. I'll be using SV for the inventory at V. But if we just arbitrarily put yellow on the left and red on the right at V, then you can see that this edge will be colored in a way that's not allowed. So what we did is we decided for each vertex V, we're going to look at all of its left neighbors. We're going to look at all of the conflicts on the edges joining V to its left neighbors. And we're going to delete any colors from the inventory at V that might contribute to these conflicts. So for example, I showed you that based on the current inventories, there's a potential yellow-red conflict between V and that leftmost neighbor. So what we do is, since red is involved in a possible conflict, we're just going to delete the color red from the inventory at V. If we do this for every vertex, then we see that each vertex gets a reduced color inventory. And if we use the reduced inventories to arbitrarily assign each vertex a color, then we will no longer have a risk of accidentally coloring an edge like its conflict. So this is why we do these reduced inventories. It's to get rid of possible conflicts. So when we're making these reduced inventories, we have to think, what could possibly go wrong? What would prevent us from getting to this single conflict coloring at the end? Well, one thing that might happen is we might accidentally delete all of the colors from a vertex's inventory. For example, remember these color inventories are completely random. So one thing that could happen in this situation that I showed on the previous slide is we could just give the inventory red-blue to the vertex V, and then maybe the color red would appear at that middle vertex and the color yellow would appear at that left vertex. And in this situation, our rule for creating these reduced inventories would tell us to delete all of the colors from the inventory at V. But this is no good because our goal is to use a color from the reduced inventory at each vertex to complete a coloring. So if a vertex has nothing in its reduced inventory, then we have no way to color that vertex. So what we're going to do is we're just going to say this is a bad event. We don't want this to happen. We're just going to hope that in our random process, this type of thing can be avoided. And remember that's, yes.
Oh, sorry,
yes.
Could I ask a quick question about the
Oh,
colorings
absolutely. Absolutely.
from the Q&A? So we get to know the inventories at the other end of each edge, just from the,
Yes.
if you could go back to the previous slide, if that's
Yes.
Thank you. So this is just a question from the Q&A. So we get to know the inventories at the other end of the edge. So the red-blue conflict on the bottom edge can't happen, so we don't delete the blue in the bottom.
Yes, that's absolutely right.
Okay, so you're looking at them left to right.
Right. Yeah, so for each vertex, if you want to know what you're going to delete, you just look at its left neighbors. And you see, you pick a left neighbor and you see if both of the colors in the conflict are in those vertices inventories. So for the red-blue conflict, red does not appear at that vertex's inventory, so we don't have to worry about that.
Okay, cool. Thank you.
That's a good question. But that's actually a nice property though, because this means we're less likely to accidentally delete all of somebody's colors. Okay, so I see there are actually two questions. Should I keep going, or
I think
is there another
actually, I think
question?
they're the same question.
Oh, okay. Yeah. So we don't delete blue because red doesn't appear in that other vertex's inventory. So there's no risk of that red-blue conflict.
Cool. Thank you.
Okay, great question. Okay, so anyway, since these inventories are random, the event that all of somebody's colors get deleted is a random event. So what we can do is we can just say, let's define this thing that I have drawn on the screen as a bad event. And since this is a random event, we can upper bound its probabilities. We can bound its dependencies, and then we can try to use the Lovasz Local Lemma. And this is exactly what we did. So what we did is, remember we have a graph G of max degree delta and degeneracy D. And what we did is we chose the probability of a heads coin flip in that inventory assignment process in order to maximize the upper bound on our probability of a bad event. And what we get is that the probability of one of these bad events is at most e to the minus k squared over 4d. I know this is not at all obvious by looking at the slide, but if you do maybe, I think it was like about half a page of calculations, you can get to this upper bound. Similarly, without going into too many details, since the bad event for a given vertex V, it only depends on what happens at V and the left neighbors of V. You could say that this bad event is sort of dependent entirely on what happens at this star centered at V and including its left neighbors, as well as the neighbors of that star. So since this star that I'm describing has D plus 1 vertices, V and its D left neighbors, and since each of those has at most delta other neighbors, you can upper bound the dependencies of bad events with D plus 1 times delta. And finally, we just need to apply the Lovasz Local Lemma. So what we do is all we need to do now is we just need to make K large enough so that P times D is at most 1/4. And then the Lovasz Local Lemma will tell us that our single conflict coloring must exist. So if you do a little bit of calculation, you'll find out that a K, which is of the form about root D log D delta, will be large enough in order to make P times D be at most 1/4. So in this way, the Lovasz Local Lemma gives us this nice upper bound, which gives a yes answer to that question of Dvořák, Esperet, Kang, and Ozeki. Okay, so the point of me showing you this result is, one, I'm quite happy with this result. I was really happy when Tomasz and I found this. And also, this should show you that the Lovasz Local Lemma doesn't have to be some trivial thing where you just do some random process in the most obvious way and then compute P and D. There is still quite a bit of room for creativity in how it's applied, which means that the Lovasz Local Lemma can be used to get some very nice and non-obvious results. Okay, so the next problem that I'd like to talk about is a similar problem called cooperative coloring. And the first paper in which I was able to find the term cooperative coloring was written by these 5 authors on the screen. But this problem is actually a little bit older than those authors, or it's older than that paper, I should say, because if you know what an independent transversal problem is, this is an example of an independent transversal problem. And many of the results in cooperative coloring come from the more general study of independent transversals. But anyway, to define what a cooperative coloring is, in this setting, we have a set of vertices on which many graphs live. We're going to call these graphs on the common vertex set G1 through Gm. And our goal in this problem is to choose an independent set from G1 and then an independent set from G2, all the way up to an independent set from Gm. And we would like the union of all of these independent sets to be equal to our universal vertex set. So for example, if you look at this picture here, I have 2 graphs on this common vertex set. One is the graph with red edges, one is the graph with blue edges. And you can see if I choose those two blue vertices, they make an independent set in the blue graph, and then those two red vertices make an independent set in the red graph. So together, those two independent sets form a cooperative coloring. And the reason this is called a coloring problem is so you can imagine if you have a single graph G and you want to know if it's K colorable, you could turn that into a cooperative coloring problem where you just take K copies of the graph G, put those K copies on the same vertex set, and then any proper coloring of your graph G will correspond to a cooperative coloring. The word cooperative and proper sound similar, so I forget which one I said first. Any proper coloring of G will correspond to a cooperative coloring of your K copies of G, and your color classes will be those independent sets. So also I should point out, rather than saying that the graphs have indices 1 through m, it's often easier just to say that the graphs have different edge colors. And then instead of choosing independent sets, you're just coloring the vertices so that no edge has both of its endpoints colored with the same color as that edge. Okay, so this is the setting of the cooperative coloring problem. In this recent paper that I cited from Aharoni and those other 4 authors, what they considered is what happens when each of these graphs, G1 through Gm on the common vertex set is a forest, so that it has no cycles. And what these authors found is that for each positive integer delta, there exists a value mf delta such that if each of your graphs Gi in your family is a forest of max degree delta, and if you have at least mf delta forests in your family, then a cooperative coloring on that family of forests must exist. And you can just think intuitively, if I have this one set of vertices and I keep adding more and more graphs to this family, then that gives me more and more opportunities to choose independent sets that will cover all of the vertices. So of course, if m is larger, then that makes coloring easier. So this mf delta is like the best possible lower bound that you need for the number of graphs in your family in order to get a cooperative coloring when they're all forests of max degree delta. So they proved that this parameter mf delta exists. In particular, if you have sufficiently many forests of max degree delta on your common vertex set, then a cooperative coloring must exist. And what they were able to show is that this mf delta has some asymptotic bounds. Specifically, they were able to show that this mf delta is at most about log delta, and it's at least about log delta. So what this upper bound means is if you take more than about log delta forests of max degree delta and you put them all on a common vertex set, then they must admit a cooperative coloring. And what this lower bound means is there exists a set of about log delta forests of max degree delta on a common vertex set that do not admit a cooperative coloring. But this upper bound and this lower bound are quite far away from each other. And what I was able to do is I was actually able to make 2 improvements to this result. The first improvement that I was able to make, I guess it's not so much of an improvement as a generalization. But what Tomasz and I noticed in our previous result about single conflict colorings is that result can actually be used to imply that this upper bound of big O log delta, this holds not only for forests of max degree delta, but any family of graphs of max degree delta with bounded degeneracy. So that was one way that I was able to get something slightly better. But the other way that I was able to get something better than this result is I was able to find a construction that improves this lower bound of log delta. So what I showed, which I'll sketch here, is that this lower bound is actually at least about log delta over log delta. And what that means is there exists a family of about log delta over log delta forests on a common vertex set, where all these forests have max degree delta, and these forests do not admit a cooperative coloring. And this works for any delta, but obviously the larger delta is, the closer this coefficient gets to 1. And the way that I was able to show this is with this following type of construction. So what I started with was this family of 2 forests on 5 vertices, and that's what's shown at the top in that picture. There's a red forest and a blue forest, and as you can see, those 2 forests do not admit a cooperative coloring. You can show that by case analysis, or you can say there must be a blue vertex somewhere on the left, there must be a red vertex somewhere on the right. So there's nothing available to color the middle vertex. But when I have this family of 2 forests that do not admit a cooperative coloring, it's possible to blow this up to a family of 3 forests on a larger set of vertices, where these 3 forests do not admit a cooperative coloring. And the way that we can do that is we would like to go from graphs indexed by just red and blue to graphs indexed by red, blue, and green. So essentially, we would like to add a 3rd graph, which is green. So what we're going to do is we're going to copy this construction with just 2 forests, and we're going to give it 3 copies exactly. And in the first copy, we can shift the colors so that red is avoided. In the second copy, we can shift the colors so that blue is avoided. And in the 3rd copy, we can shift the color. Actually, we don't have to shift the colors at all. If we just leave the colors the way they are, then green is avoided. And what we can see is that since these 2 graphs do not admit a cooperative coloring with just those 2 colors, in this first copy that we have here, the color red must be used somewhere on one of those vertices. Because otherwise, if red were not used anywhere there, then those 5 vertices in that first copy would have a cooperative coloring using just blue and green, but that's not possible. So red must appear somewhere in the first copy. Similarly, blue must appear somewhere in the second copy, and green must appear somewhere in the 3rd copy. But after all of that, if we add one more vertex, which is a universal vertex that's adjacent to every vertex in the first copy in red, everybody in the second copy in blue, and every vertex in the 3rd copy in green, then we can see that no color will be available for that last vertex. And this gives us our family of forests. Now it's a family of 3 forests and not just 2. And this family of 3 now does not admit a cooperative coloring. And you can use your imagination and think, now that I have a family of 3 forests that doesn't admit a cooperative coloring, if I want to add one more, let's call it yellow, I can make 4 copies of this construction that I have now, make 1 copy avoid red, make one copy avoid blue, make 1 avoid green, make 1 avoid yellow. And then you can add 1 universal vertex that joins to those 4 copies respectively in red, blue, green, yellow. And that will give you a construction of 4 forests that doesn't admit a cooperative coloring. You can just keep repeating this to make your family as large as you want without admitting any cooperative coloring. Now, if you take that construction and you compare the maximum degree to the number of forests in the construction, then you'll get the relation that the number of forests is about log delta over log delta. So this improves that lower bound of Aharoni and those other 4 authors. But one interesting thing about this construction is that if you look at each forest in the construction, they are all star forests. Specifically, if you look at the vertices with red edges, every component consists of a center vertex and then just a bunch of leaves. Similarly for the graph on the blue edges and similarly for the graph on the green edges, every component is just a center with a bunch of leaves. And if a forest has every component consisting of just a center and a bunch of leaves, then we say that it is a star forest. So this leads to a very natural question. We had this upper bound of about log delta for the number of forests you need in a family of max degree delta to guarantee a cooperative coloring. If we know that all of our forests are star forests, can we make this upper bound of log delta a little bit better? And the answer is, actually, I don't have that on this slide, but the answer is going to be yes, we can make this upper bound a little bit better. And the idea for how we're going to do that is, again, using the Lovasz Local Lemma. So before I start applying the Lovasz Local Lemma, I just want everybody to make an observation. If we have a family of star forests on a vertex set, then at each vertex, you can consider all of the possible colors that you could use to color that vertex. And you can say that each color is either a center color or a leaf color. And if I look at the vertex at the top, for example, I would say blue is a center color because that vertex is the center of a blue star. However, I would say red is a leaf color because in the red star containing that vertex on the top is a leaf. It is not in the center. So at that vertex on the top, since it's the center of the blue star, but it's a leaf in the red and yellow stars, I would say that blue is a center color and red and yellow are leaf colors. Similarly, that vertex on the left has yellow as a center color because that vertex is the center of the yellow star, but red and blue are leaf colors because that vertex on the left is a leaf of the red and blue stars. And this idea of center colors and leaf colors will be very useful. One observation we can make immediately is that if each vertex has at least one leaf color, then since just the sets of the leaves in the stars are all independent sets, then we could just give each vertex one of its leaf colors, and then we could give this graph family a cooperative coloring. So in the worst case, where it's hard to find a cooperative coloring, there must be some vertices that have a lot of center colors. So what we can do is we can consider the worst case, and we can think, let's just try to color the vertices of this set that contains all of our graphs, and let's try to color them randomly and apply the Lovasz Local Lemma. So what we can do is we can define a set U of vertices that have many center colors. I'm going to say many means at least epsilon times m, where epsilon is going to be just some constant that's small but not zero. And remember, m is the number of graphs in our family. So U will be the set of vertices with many center colors. If U is empty, we can just give each vertex one of its leaf colors and then we're done. So we assume that U has at least one vertex in it. Then what we're going to do is for each vertex in U, we're going to color it randomly with one of its center colors. Then what we would like to do is just take the remaining vertices and arbitrarily color each one of them with one of its remaining available leaf colors. And if each vertex outside of U has at least one remaining available leaf color after this process is done, then just arbitrarily coloring each remaining vertex with an available leaf color will complete a cooperative coloring. So let's take a look at when this might not be possible and how we can use the Lovasz Local Lemma to try to show that when M is large enough, we can always get a cooperative coloring. So what we can do is we can say the only thing that might prevent us from getting a cooperative coloring on our graph family is if we have a vertex like V. If V has lots of leaf colors because it is not in the family U, but many of the neighbors of V have a lot of center colors, and these vertices are in the family U. Specifically, each of these neighbors of V, they will have at least epsilon times M center colors, and therefore they'll be in the family U, and they will be colored on the first random step, and they might potentially take away leaf colors from V. For example, in this picture here, if we look at these 5 neighbors, one bad thing that might happen is we might accidentally color that vertex on the left purple, we might accidentally color the upper left vertex green, the top vertex red, and so on, and that would take away all of the leaf colors from V. However, the probability of this actually happening is going to be quite small because the probability that each of those troublesome colors is chosen for each neighbor of V is going to be at most 1 over epsilon M, because remember, each of these vertices has a lot of possible center colors to choose from. Furthermore, since V is not in U, V is going to have a lot of leaf colors that need to get taken away to cause a bad event. So the probability of V losing all of its leaf colors is actually at most 1 over epsilon M to the power of 1 minus epsilon M. And this is going to be very small. Furthermore, without going into the details, we can upper bound the dependencies of one of these bad events. It's just going to be M, which is the number of our graphs, aka number of colors, times delta. And finally, all we need to do to apply the Lovasz Local Lemma is we just need to choose a value M so that P times D is at most 1/4. So it turns out that if we make M just a little bit bigger than log delta over log delta, then P times D is at most 1/4, and our cooperative coloring must exist. So if we take this M value, which guarantees the existence of a cooperative coloring, and we compare it to the size of this family, which does not have a cooperative coloring, you'll see that they're actually the same, besides the fact that this little O1 term could be positive or negative, or it could be doing different things. But what this tells us is that if we just care about the number of star forests needed to guarantee a cooperative coloring, the correct asymptotic bound for this number of star forests is exactly 1 plus little o1 log delta over log delta. And it was shown just using the Lovasz Local Lemma with a slightly non-obvious random process. Okay, so to conclude this talk, because I know I'm almost out of time, I hope that this talk has shown you that the Lovasz Local Lemma, despite being a very simple statement, it does have a lot of room for creativity. It can be applied to many types of problems. And no matter what area of combinatorics you're researching, you can probably use it too. So I recommend that everybody in your research, if you don't already do so, you should definitely at least try to use the Lovasz Local Lemma. All right, thank you.
Thank you very much, Peter, for a fantastic talk. Everyone, yeah, send your rounds of applause to Peter. That was incredible.
Thank you. Thank you.
All right. If anyone has any questions, feel free to throw them in the Q&A part of the chat. We have one from Mark who says, if you have one vertex and two vertex stars, how do you define leaves and centers in the cooperative colorings?
Okay, so
I think a couple of slides back.
Right. So so essentially in this problem, you have graphs 1 through m, and 1 through m are also like colors that you can use to color each vertex. So at each vertex, you're going to partition that color set 1 through m into a set of center colors and leaf colors. So if I look at color I and I want to know if it's a center color or a leaf color, I will look at the star of edge color I that contains my vertex. Now, if this vertex is a center in the star of color I, then I say that I is a center color. If it's a leaf in the color, a leaf in the star of color I, then I say it's a leaf color. So wait, let me look at the question again. For one vertex and two vertex stars, how do we do? So if like for this vertex in the middle here, if it were the center of a red star and a blue star, for example, you would say red and blue are both center colors, and then the other colors would be leaf colors. So does that answer your question? So I didn't want to take too much time at the end, so I did go kind of fast. So I apologize for anybody who got lost.
Howdy. Thank you. That doesn't quite answer my question. My question was, if I have a forest of stars,
yes,
then some of my stars can have, like maybe I've got like one big star, but then I've got some isolated vertices, which are still stars.
Yes.
They're just named stars. Is an isolated vertex, is that a center or a leaf?
Okay. Yeah, I kind of brushed over that. If it's an isolated vertex, you can just call it a leaf. The property you want with leaves is like if you take the red forest, you want the set of all of its leaves to be an independent set. That's really all you care about. So if you have isolated vertices, you could say they're all leaves. Now, if you have a K2, you'll have to say one of the vertices is a center, the other is a leaf. It doesn't matter which is which. But
okay. You just define, rooted forests or whatever, and do this process. Okay.
Right.
Okay, thank you.
Yeah, you're welcome. That's a good question. Yeah, I did sweep a few details under the book.
It's a talk. That's expected.
Yeah.
Are there any more questions? I've actually got one. So for the single conflict coloring, this idea that you use these inventories for each, in this slide.
Yes.
So you define these inventories, and then you sort of use the degeneracy to show that every vertex has at least one color left in its inventory at the end. Right. What goes wrong if you just try to use the Lovasz Local Lemma with some like super naively, like you just colored the graph directly? What falls apart?
That's a great question. So what falls apart is, well, nothing falls apart. You just get a different upper bound, and that upper bound is scaling, I think, of root 2e delta, or maybe delta minus 1. It's about 2e, root 2e delta. So that's great if you just want an upper bound in terms of the maximum degree. But like if you want to get into the details of why you get something in terms of delta and not d, the reason is that in the naive random coloring procedure, the probability of a bad event is just 1 over k squared. Yes, 1 over k squared, where k is your number of colors, because you just have one conflict. The probability of getting that conflict is 1 over k times 1 over k. And then your dependencies are going to be something linear with delta, and the degeneracy doesn't show up anywhere.
Yeah, okay.
However, if you say that this is your bad event, then well, okay, it gets kind of hard to explain quickly, but essentially the probability of this bad event happening is like 1 minus p to the probability of something with d in it.
Yeah, okay.
And then that ends up just being a lot smaller and working out a lot more nicely.
Okay, so you sort of get a bit of a bonus, both in terms of the number of events you're dependent on and in terms of the probability of a bad thing happening.
In terms of the dependencies, it's you get d plus 1 times delta instead of about 2 delta. So like it's roughly different, but you get a much better upper bound for your probability.
Okay, cool. Any more questions? All right, well, if not, well, then let's thank Peter Bradshaw again for a fantastic talk.
And thank you, everybody. I really appreciate it.
And I
And I
believe
appreciate the questions too.